Hello everybody, here we are again. Chapter 15 is touching one of the probably most vast topics in the last years, because it opens clearly a lot of possibilities. So here we discuss about size optimization, shape optimization, and topological optimization. But more than any word, we go through an example, practical one, very simplified of course, but taken from motorsport. So this could be a Formula 1 monocoque from the first 2000 years, early 2000s, and design space is generated. We can use 4-node tetrahedron to prepare the topological optimization and to fill up the design space. Then we freeze some points, engine attachments, for example, and suspension attachments. So these cannot be touched during the topological optimization, and we want to optimize the torsional stiffness. Clearly, as I said, it's very simplified. Many other load cases need to be considered into an F1 chassis, but this is just to show, maybe also in a provocatory way, seeing the results we obtain. So topological optimization, it's run and we get 3 different structures depending on the density that we want to keep. And then of course the extraction of the model is done, one of the 3 is chosen, and the calculation is repeated to check the real actual stiffness and to check the stresses. Clearly these need to be engineered in the sense that this is exactly what we get from the topological optimization, and we need to be rationalized, so to say. But then what happens if we consider, instead of a tubular structure, the result that is coming out, something which is obtained by metal sheets welded together? And using, in this case, size optimization, in the sense that the thickness can vary between 2 values, minimum 1, which will be something under which we cannot go because of technological reasons, and a maximum 1 maybe coming from the fact that we cannot have sheets above a certain thickness for the material we are considering. We started with aluminum, just to homogeneous material, just to see. And then we calculate also the, let's say, efficiency index, so the ratio between the mass and the stiffness, or vice versa, the stiffness and the mass. And we see that the metal sheet welded is for sure worse than what we obtain here, but we can think of using still the metal sheet approach, but putting some ribs in the position where the topological optimizer has put the material, so to say. So using the topological optimization to somehow drive a different concept of the structure. And this starts to be better, of course, because the connection between inside and outside is there, and it making it stiffer and lighter. Coming to a certain solution which might be even better than the one we got from the topological optimizer. And then we build up a very, very, very simple layup of the part, and we fill the thickness, we fill it with foam, and then we have 2 skin, an outer skin which is thicker and an inner skin which is thinner. And it is all over. So it's, as I said, it's not optimized, but what we find is that it is possible that the carbon solution is not the most efficient, and maybe if in the future there will be 3D printing machines able to generate such a structure with in terms of dimension, and the possibilities offered to the thickness to be continuously varying, might change the construction philosophy of one-seater competition car, so to say. It's just, as I said, a suggestion and a hint on how to deal with structural optimization, we need to be clearly open-minded and not have any prejudice. So, that's all for chapter 15. Chapter 16 will be quite interesting and challenging as well, but as we will see in the next appointment. Goodbye, everybody.